All right, this video is just going to do a little bit of cleanup on reactions of esters. We've already talked about creating esters, and we talked about a couple of their reactions as far as saponification and hydrolysis. But now what we want to do is get a little into some more, some reactions that we actually have already discussed and we've already seen before in this course, and that's reduction of esters with lithium aluminum hydride, and also the reaction of esters with Grignard reagent. And then what we're going to do is we're going to talk about amides and what chemistry amides do. Once we've created amides, there are a few different reactions that happen. Remember that amides are some of the least reactive of the acid derivatives, but there is some unique chemistry, and we'll talk about that. And so once we've created amides, we'll do some hydrolysis reactions of amides, we'll reduce amides, and then when we reduce them, we'll create amines, and then we'll dehydrate amides with SOCl2. When we dehydrate an amide, we'll create a nitrile, and then there's going to be some reactions of nitriles that we'll discuss as well, namely the acid and base catalyzed hydrolysis of nitriles. And so let's go back and clean up a little bit of stuff with esters. And so I just want to start with an ester. There's some reactions that I think we already know. And we know that if we take an ester and we react it with excess lithium aluminum hydride and then treat with water, then we create a primary alcohol. And we actually already know this mechanism as well, but in order to review it thoroughly, we start off with aluminum hydride. And remember that aluminum hydride is a hydride delivery agent. And for the most part, hydride acts as a nucleophile. Going to create a tetrahedral intermediate. And under these conditions, I can expel an alkoxide, and that's what I do. And I form an intermediate aldehyde. I think we talked about this before, and that with lithium aluminum hydride, the intermediate aldehyde cannot be isolated, and so hydride goes along and reacts again. Creating the intermediate alkoxide. And then upon treatment with water, we create hydroxide and our primary alcohol. Now, with lithium aluminum hydride, we cannot isolate the intermediate aldehyde, but we can isolate an intermediate aldehyde if we use a hydride delivery agent that is somewhat sterically hindered and thus reacts more slowly with the aldehyde, and that allows the aldehyde to be isolated. This is diisobutyl aluminum hydride, and that looks like this. So we have isobutyl. That's diisobutyl aluminum hydride. And then with this reaction, we can isolate the intermediate aldehyde. I think we've discussed both of those reactions in the past, and another reaction that we've discussed in the past that helps us clean up with esters is the reaction of Grignard reagent with esters. We certainly discussed this in the alcohol chapter. If we use excess RMGBr, let's make that an R prime, and then react it with a proton source, whether that's water or acid. In this case, I don't think it matters. We end up with a primary or an alcohol that has two new R groups attached to it. So we end up with a tertiary alcohol. And again, we do know this reaction mechanism. Remember that the R group in this case is negatively charged. So the R group attacks the ester. It forms a tetrahedral intermediate. Let's make that R prime so we can see it. O minus. And under these conditions, again, which are basic, I can kick off the alkoxide, and that's what happens. It reforms the carbonyl group and creates a ketone. Ketone is not isolated, but reacts with another equivalent of Grignard reagent. In the standard Grignard mechanism. Again, another tetrahedral intermediate is formed. And now the proton source comes along in a second step after we've isolated the salt. And that's what forms the tertiary alcohol. Okay, and so that's just a little cleanup with esters. I think we've seen all of those reactions before. And so now it's time to discuss amides, the last of the acid derivatives. We've already discussed acid chlorides and acid anhydrides. They're the most reactive. We've discussed esters. They're a little more reactive than amides. Amides are the least reactive, although they have a bit more interesting chemistry that's going on. We do already know how to create amides, and that's the reactions. The most efficient way is to react ammonia or other amines with acid chlorides to form amides. And so there's not much new going on there. We haven't, though, I don't think, discussed hydrolysis of amides. And that's if you react an amide with acid catalyst and heat, then you can form a carboxylic acid. And maybe we only discussed the reaction, and if we did, we didn't discuss the mechanism. And so let's take a look at the mechanism now. If we have H3O in solution, the H3O can protonate the carbonyl group. And once the carbonyl group is protonated, that carbon is more reactive to nucleophile. And so I can attack the carbon with water. I'm going to flip it over now. To form an intermediate, a tetrahedral intermediate. The mechanistic steps of this hydrolysis mechanism are analogous to the hydrolysis of esters. Proton transfer, nucleophilic attack, proton transfer. This is going to create a neutral intermediate. And I'll need another proton transfer so that the nitrogen is ready to leave. And the nitrogen, the ammonia is ready to leave, I should say. So that becomes NH3 plus, which is now ready to leave. And one of the carbonyl groups, or one of the alcohol groups, will reform protonated carbonyl, kicking off ammonia. And now that I have ammonia in the solution, that is a base, and that's what will react with the protonated carbonyl to reform the carboxylic acid. And so take a look at amide hydrolysis, proton transfer, nucleophilic attack, proton transfer, loss of the leaving group, proton transfer. The exact same steps as acid catalyzed hydrolysis of esters. Only slight variations in some of the steps, as in what are actually the species that are leaving and serving as the final reagent that does the proton transfer. Okay, let's take a look at that. Now that we've talked about hydrolysis under acidic conditions, there is also hydrolysis under basic conditions. So we can use sodium hydroxide, heat. Here's the reaction you should know. Finishing it off with another proton transfer with some acid, and we end up with carboxylic acid as well. I think we showed hydrolysis of esters under basic conditions, and we're going to see a similar situation here. Hydroxide can immediately attack the partially positively charged carbon and form the negatively charged oxygen, because that's basic conditions, and that's where we are as far as the reaction is concerned. We're in basic conditions, so that's not going to be any problem. Now, what comes next is that I have to get rid of the amide group, and I can do that without reprotonating it into something neutral, because it does, again, expel a base. But it is a very strong base, and it immediately reacts, again, the same way as it did with ester. It immediately reacts with the carboxylic acid that had been formed in the previous step to form carboxylate. And now that I have carboxylate in my next step, I can use acid once it's been isolated to form a neutral and isolatable carboxylic acid. For the next reaction, I'm not going to show a mechanism. But I am going to show the reduction of amides with lithium aluminum hydride. What's going to be different about this mechanism from the other ones is that the oxygen is completely removed. And I'm just left with an amine. I'm left with a primary amine. The oxygen is completely removed, and I am left with only an amine. Okay, the last derivative that I want to discuss is along with amides, but it's the formation of nitriles. Now, I don't have to use an amide to make a nitrile. I'm going to show you a reaction where I do, but I want to remind you of one of those reactions that we did in Organic Chemistry 1, where I reacted a primary alkyl halide with sodium cyanide, and I formed a nitrile this way. In Organic Chemistry 1, we talked about this being an SN2 reaction with all the normal SN2 considerations that apply. But what we said about this was that it's not in Organic Chemistry 1, it wasn't particularly useful from a synthetic point of view because we didn't know what to do with nitriles. And now we've already developed some things. We can reduce the nitrile into an amine. We know how to do that already. And we'll see some other reactions of nitriles as well. So let's go ahead and start off with another way to create nitriles. Here's another reaction. And that's dehydration of an amide with SOCl2. So there's another example of a reaction that you should know. And this will form nitrile. All right. The other products are SO2 and HCl. Okay, we've gone through a similar mechanism, but now I want to apply this SOCl2 mechanism to the amide. So starting with amide, I'll remind everybody what SOCl2 looks like. That's what it looks like there. And we have a similar starting off point. This time, though, it involves the nitrogen instead of a oxygen group. I form a partially positively charged nitrogen. And here's this oxygen connected to the SOCl2. Electrons are still there. Okay, now I need to pop off that chlorine, just like I did in the reaction with carboxylic acids, in order to form an acid chloride. And I'm going to get this intermediate. Now, we talked about when we were forming acid chlorides that this is a good leaving group, and that's still the case here. So what we're going to do, though, is we need to form the triple bond on the between the nitrogen and the carbon. And so this is when we get some base deprotonates the nitrogen, forms the triple bond, makes SO2 while popping off the CO. This gets us R, C, triple bond end, plus SO2 plus Cl minus plus whatever our protonated base is. And this is where the HCl comes in. Okay, this is what creates a nitrile. So the reaction with SOCl2 and amides is very much analogous to the reaction of carboxylic acids and amides. But now that I have nitriles, what can I do with them? Well, we've already talked about reducing them into amines, but here's something new. I can react it with acid and heat, and I can not oxidize it, not quite oxidize it, but I can transform it into an amide. And then we already know that under these conditions, the amide will also undergo hydrolysis, and the final product is carboxylic acid. And so if I were to put it on the reaction board to say, here's a reaction that you have to know, I would write nitrile with acid and heat forms carboxylic acid. Let's take a look at this mechanism. So if I start with a nitrile, how do I get to a carboxylic acid if I'm reacting it with H3O+? In this case, I'm going to protonate the nitrogen. This is something a little bit different than we've done before. I can actually show resonance here. That the carbon should have a fairly significant positive charge character. And that's where I'll get water to attack. And we can show this without the resonance and show the water attacking directly and the electrons moving over from the nitrogen, whichever way you prefer to see that. Okay, from here now the product is this guy. So the positive charge is shown on the oxygen. And I need to come along and deprotonate this. To form this intermediate the lone pair on the nitrogen is still fairly basic. Will react with acid and protonate itself. And once it's done that, we can also again show resonance. And now we're showing it as a protonated amide. And I can do a final proton transfer to get to the amide. Now, once I'm at the amide, everything else happens just like it did before with the acid catalyzed hydrolysis of amides in order to go all the way to the carboxylic acid. And so I've got proton transfer, nucleophilic attack, proton transfer, let's make sure I got this right, proton transfer, nucleophilic attack, proton transfer, proton transfer, proton transfer. Then it's proton transfer, nucleophilic attack, proton transfer, loss of a leaving group, proton transfer. So the entire process of going from nitrile to a carboxylic acid involves 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 steps. The last 6 steps, though, you already know from acid catalyzed hydrolysis of an amide. So I'm not going to bother to show those here. Okay, what else can we do with nitriles? Well, that was hydrolysis of nitriles under basic conditions, or excuse me, under acidic conditions. And now what I want to do is I want to show hydrolysis of nitriles under basic conditions. And so the reaction would involve sodium hydroxide in water like before, and then a final step of adding a proton back onto it, and I will get me a carboxylic acid. Now, we've got some similar reaction mechanisms going on here. And I've got hydroxide in the solution now. It's basic. So hydroxide is going to actually attack that carbon immediately. And that's going to form a negatively charged carbon, or excuse me, a negatively charged nitrogen. And that nitrogen will then react with the water that's just formed and protonate itself to reform hydroxide. We've seen this guy before, but what we haven't done with it is used the hydroxide that's formed to debrotonate the OH group. That forms a negatively charged oxygen, and we can again show some resonance where the negative charge is delocalized onto the nitrogen. And once I've done this, I form an amide. Now, we've already talked about hydrolysis of amides under basic conditions. And so the amide goes on to react with hydroxide, as we've shown before, to form carboxylate. And then that's where the next step comes in, and we react carboxylate with the acid. So we have some new steps: proton transfer, proton transfer, proton transfer, proton transfer. So a series of proton transfers. I'm sorry, the first one is not proton transfer. That makes sense now. That's nucleophilic attack, then proton transfer, proton transfer, proton transfer. And then if we were going to do follow up with the base catalyzed hydrolysis of an amide, it would be nucleophilic attack, loss of a leaving group, and then finally a proton transfer to follow everything up. And so we have a combining mechanism that we already know from the past. We can create a little bit longer of a mechanism, taking a nitrile all the way to a carboxylic acid. All right, let's see. There's a couple of just last reactions to sort of polish up and make sure that we're all good with nitriles. You know, nitriles will also react with Grignard. Except in this case, it forms ketone. Okay. And nitriles will also react with lithium, aluminum hydride. This is the reaction that we already know. And this will form amine. Okay, well, this is what wraps up carboxylic acids and their derivatives. So we talked about them in order of their reactivity. We created acid chlorides. We talked about their reactions. Then we created acid anhydrides. We talked about their reactions, and it turns out they're essentially the exact same reactions as acid chlorides. Then we talked about esters and their reactions. Not a lot of stuff going on there. Then sulfonification and Fischer esterification is definitely something. And then we also talked about amides. Then amides transitioned smoothly into a conversation about nitriles. And so that concludes all of the chemistry that's involved with carboxylic acids. And so we're going to move on after carboxylic acids and talk about the alpha carbon from carbonyl groups. That's the carbon next to the carbonyl carbon. And we're going to talk about all the chemistry that happens there. So the carboxylic acid starts the conversation about the reactions of carbonyl groups. Actually, the aldehydes and ketones chapter starts that conversation. So from aldehydes and ketones, we talk about all the different nucleophiles that aldehydes and ketones react with, and all of the reactions of carbonyl groups. Then we expand that into a conversation about carboxylic acids and their derivatives. It's essentially still a conversation about carbonyl groups. Then after that, the next thing we're going to talk about is we're going to talk about one carbon over from a carbonyl group, and that's the alpha carbon, and that's what's coming up next. So the last bit of organic chemistry too, a large portion of it, is really a conversation about carbonyl groups and the chemistry associated, or the chemistry that happens because there's a carbonyl group there. Ultimately, alpha carbon chemistry happens because of the carbonyl group, and we'll see that as we move in to the next bit. And that's all for now with carboxylic acids. We'll see you for some problem solving.